Here we have a wheel or a disc of mass m and radius r, and there's a force P applied at the top, and it's going to cause the wheel to roll forward. And we're asked to find the acceleration of the center of the wheel, g, and the mu s minimum to keep it from slipping. So we can start with a free body diagram. We've got P acting at the top. We'd have an mg here. We have a normal down here. And then we have friction. And which way does the friction act? Would the friction act to the front in the direction of motion, or would the friction act to the rear? Well, I think it's going to act towards the front. And we'll just call it F because we don't know if we're at the maximum or not. F sub S. And if we're wrong with our guess, it'll come out to be negative, and we'll show that later. And that completes our free body diagram, and now we're ready to apply the equations of motion, which we know are all of these, where we have one linear equation that we can apply, and then three forms of the moment equation. This one's very handy. We use this one quite a bit because it's short. These other two are handy as well. You can take the moment about any point and make sure that I of A and A of A lines up, or down here that I of G, A of G line up. Let me start with the one that looks easier. Sum of the moments around G is equal to I G alpha. And we'll define for this problem this as all of our positives, so that'll be a positive in the x. We'll use this for a positive in the y. And I'm going to call clockwise positive only because I can see that this is going to rotate in a clockwise fashion. And I don't want to trace too many negatives around. So using that convention, we have P times R minus F times R is 1/2 mr squared alpha. Here some of the r's go, and we get alpha is P minus F times 2 over mr. So that equation is handy. The downside is it has both of our variables in it, and that can take a little bit of extra work. Let's see what the other equation might have looked like. We could have tried some of the moments about C, the contact point down here, would be IC alpha plus MRG cross with AC. Now, if we're looking for mu s minimum here, that means that it's not going to slip, and therefore the acceleration of point C would be 0. It doesn't move. It's the wheel rolling without slipping condition. So that's 0. Turns out this equation is not so bad. If we take the moments about C, we end up with P times 2R is, now we need the I about C of a wheel. We can find that quickly over here. I about C at the bottom would be 1/2 mr squared plus, our offset distance is r, and that would be a 2 over 2. So we're going to get 3/2 mr squared for that. So we have 3/2 mr squared alpha. This r goes, and we'll get an alpha of 4p on 3 mr. And the main reason that this is a little bit nicer is it only has one of our variables in it instead of both at the same time. They're both valid. If you substitute one into the other, we can prove that, but it's nice to have them both here. Now that we've developed those equations, we need to relate the forces linearly, and we do that as usual with the sum of the forces is equal to ma about g only. So agx will be p plus f over m. And in the y direction, there's not much happening. Ay is 0, so we see that n would simply be mg from that axis. There's no upward acting force trying to lift it or anything like that. Now, what we have here is we have information about a sub g, and we have information about alpha, and again we have to relate these two. And the best way to relate them is with a relative acceleration equation. So we can say a of g will be a of c plus a of g with respect to c. And we like this because it's fixed. So a of c is 0, and we find that the acceleration of g will be the observed acceleration from g with respect to c. A of g is this. It's p plus f on m, and it's in that direction. Now g with respect to c, again, let's just sketch this out over here. So here's g, here's c. So g with respect to c is up. And the acceleration would be an r alpha type, and this is the direction of r alpha. So it's going to be an r alpha in that direction. So it's equal to r times alpha, which we could use either form here, and I certainly like this one a little bit better. We have 4p over 3mr. The r's go over here. These m's go. We can bring the 3 up to here. Clean this up. And we'll get 3p plus 3f is equal to 4p minus 3p. And we'll get p is equal to 3 times the friction force max. That's our max. And we know that friction in this case is mu n, which will be mu mg. So p max will be 3 mu mg. So mu minimum, to keep it from slipping, will be p over 3 mg. So if they tell us what value of p they're pulling on this thing with, that's how much friction we would need to have. For example, if p were equal to mg, it's a fairly large amount of force, the minimum amount of friction to keep us here would be 1/3 in that case, which is a very reasonable amount of friction. If you look at the maximum condition, let's say that mu max, the largest mu that we'd really expect to see would be 1, so p max could be 3 times mu mg, so it would be 3 times the weight. So we could pull at the top of this thing with 3 times the weight and not have it slip and then accelerate forward, which is what that tells us. So this gives us our function for finding the minimum amount of friction to keep it from slipping when you pull on it. Let me quickly just show what would happen if we had guessed friction to be in the wrong direction, because this is often something that worries people, that they have to pick the right thing right off the bat. Let's assume it was in this direction. That would make this a minus down here. And agx would still be equal to r alpha that we had before. So p minus f would be m. It would be r times this alpha, which is 4p on 3mr. The r's go, the m's go, and this 3 comes up, and we get 3p minus 3f is 4p. Bring this over as a minus 3p, and we get p is equal to negative 3f. So the minute we get a negative, we know that our guess was wrong and it should have been in this direction. So even if we had guessed wrong, it would still fix itself when we got to this point, and your answer would still be valid. To understand what's really happening down here with this friction force, let's have mu be 0. Let's have no friction. And let's see what happens to this wheel under the case of no friction. I think it'll be clear that when you pull on it, the wheel is going to slip in some fashion here. And as a result, our equation, sum of the moments about C, is IC alpha plus MRG cross A sub C. That's not 0. We don't know what that is, so let's avoid that equation. And then we would want to use sum of the moments about G is IG alpha. And we'd have, with respect to G, P times R. And now there's no friction, so there's no other forces trying to rotate it. And that's going to be 1/2 mr squared alpha, which is the eye of a disk. And we get directly from here that alpha will be 2p on mr. We can also do Newton's law, and we'd see that AGX would be the sum of the forces. Again, there's only P, and that's divided by M. That's it. And how do we relate these two? Well, the relative acceleration equation. So we can say that the acceleration of C, which is what we want to find out, we don't know it, right, is equal to the acceleration of G plus the acceleration of C with respect to G. So the acceleration of C, we know the acceleration of G, it's P on M, the positive I hat direction. Now, the acceleration of C with respect to G. We're at G and we're looking down at C. And for a positive alpha, we would have an R alpha in this direction. So that is going to be a negative R alpha. And we know alpha, it's 2p on mr. The r's go. And we end up with A sub c is p over m minus 2p over m, which is negative p over m. So the acceleration of point C in this case will be negative p over m in this direction, which is the same magnitude as p over m of the center above it as the wheel spins. So there is the slipping of that wheel. Point C is not fixed, it's sliding past the ground now at the bottom. All right, something that's interesting is we can plot this now. So G would accelerate forward with a value of P on M, and point C down here would be going backwards with P on M. What would be happening up here at point A? Well, one way to find that would be the acceleration of A would be the acceleration of G plus the acceleration of A with respect to G. And from there we have P on M. And A with respect to G, here's A, there's G, so that's A with respect to G. And for a positive alpha, we get an R alpha type acceleration out here. It's a tangential acceleration, and R is simply R. So it's in the same direction, so that's going to be plus R. And alpha was, sorry I erased it, 2p on mr. The r's go here, and we get p on m plus 2p on m, which is a grand total of 3p on m. So the acceleration of point A on top of the disk is 3 times this, which will put us out here, 3p on m. In fact, they're all linear functions. And the acceleration of any point on this wheel could be shown with that sketch there. There is a point that's not accelerating at this one instant. So as this wheel rotates and spins, that's the only fixed point that we would see above us for a second, and that would move forward and still be a fixed point from instant to instant. And that's the acceleration profile on here. But you can see at the bottom regarding friction, the wheel wants to slip in this direction. So we've got to have friction in this direction to stop that from happening and allow the wheel to roll. So now that we see it in detail, we can understand why it's acting forward and not backwards. For the last case, let's assume that there's a mu k and that it is slipping. And let's find a sub g while slipping. All right, if it's slipping, I'm going to guess that the friction's acting forward. We still have this direction for our alpha, so we'll stick with this convention down here. And thinking about it now, would you rather do some of the moments about G or some of the moments about C for this condition? And I'm thinking that the moments about C would be tough because I don't really know what A sub C is when I get to that. So I think I'm going to scratch that one. And we'll stick with this one. So using the positive direction, we have PR minus F sub KR is 1/2 mr squared. And the R's go. And we get an alpha kinetic of 2P minus Fk on Mr. So there's our alpha while slipping. Next, we could do Newton's laws. AGX would be the sum of the forces. Now, interestingly, they're both in the same direction. So it's P plus Fk on M. And then to relate these two together, we would use a relative acceleration and use the points that C is good enough. So the acceleration of C, well, that's the acceleration of G, which that's that, we're done. But let's find the acceleration of point C here in this case with friction. It would be the acceleration of G plus the acceleration of C with respect to G. That's what I'm now looking for. This we have, it's P plus Fk on M, and it's in this direction, plus, all right, C with respect to G. We're on G looking at C. We know alpha is in this direction, so that's going to be like that. And it will be an R alpha type of an acceleration, so this is minus R, and alpha we have up here as 2P minus 2F over MR. The R's go, and we'll get an A sub C now from this. Let's make this one big common denominator. So we have P plus Fk minus 2P plus 2Fk all over M, which will be 3Fk minus P over M, would be the acceleration of point C on the ground. So without too much work, we were able to find A sub G. We could have done that directly, it turns out, in one shot. We assume we would know P. Fk is easy enough to get. Fk would be mu n. And again, there's no y forces really other than the weight and the normal. So that would be mu mg directly. And we could just calculate the acceleration. So fairly straightforward there. Alpha also straightforward. Interestingly enough, though, we can find the slipping acceleration, the rate at which the wheel is slipping past the ground here at the bottom. as this. Also note that here, for P greater than 3fk, we get a negative a sub c, which is what we'd expect, actually. If our wheel's spinning and slipping, we'd expect a sub c to have a negative direction associated with it. But what's interesting is, what if P were equal to 3fk? That tells us that a sub c would be 0, which means it's not slipping. And what if P were less than 3fk? That would imply a positive a sub c, and that it switches around and goes in the forward direction, which that is not possible, so we know that can't happen. And the reason for that is we'd have to look back at our static solution that we had, and our static solution told us that P max was 3f static. So when we reach this condition down here, it would stick. It would not slip, and for any P less than that, it would continue to be a no slip event, and we'd have to go back to that solution and use those values. Also, interestingly enough, in here, all three of our solutions are valid in this equation. For mu equal to 0, f was 0, and we got an a of equal to p over m. For f sub s, this was valid with an s, and then for f sub k, it was also valid. So it turns out this one equation will give us the acceleration of point G for all three scenarios that we looked at. The alpha would also do the same thing. If f is 0, we get the 2p on mr that we had for the no friction case. And then if we plug in f sub s or f sub k, this also becomes valid. And then down here, our a sub c is also valid for all three cases. In the case, the friction was 0, and we did have an a sub c equal to negative p over m. In the case with friction static, this was 0, and we had a sub c equal to 0. In the case where it's kinetic, this becomes our solution set. So this equation also is valid for all three scenarios. So interesting interplay between friction and the rotational acceleration of a rolling disc. Thanks for watching.